Hello and welcome to this video on topic 4, which covers random variables. This will be the first video in topic 4. We start by talking about what we call discrete random variables. So let's begin. Up until now we've seen probability as a way to mathematically describe uncertainty around us. We've seen in the past that the probability of an event is estimated by the relative frequency with which an event occurs in a long series of trials. And recall we had a definition for relative frequency that simply divided the total number of times an event could happen divided by all of the possible outcomes. Now what we do is we shift to describing the probabilities of all possible outcomes, not just the probability of one outcome. And so what we're going to want to do here is think of all of the possible outcomes as variable values to which we are assigning probabilities. Now that may sound a little bit confusing at first, so perhaps what we should do is start with a quick example. Here's a table that describes the job satisfaction score of senior executives on a rating scale of 1 to 5, with 5 being the highest. So the variable values that you see here, together with the assigned probabilities that you see below it in row 2, make up what we call a probability distribution. Each variable value, such as 1, 2, 3, 4, and 5, is assigned a probability of occurring. Notice here what the probabilities add up to. If you add 0.05, 0.09, and so on through the end of the second row, you'll see that this adds to exactly 1. And this is something that we're going to see in a moment as a very important feature of a probability distribution. So let's take a look at what we're going to do with these distributions. We're going to focus at least for this course, on probability distributions for quantitative variables. It is possible to talk about qualitative variables, but for this course, because mainly what we want to get to at the end of the course is ideas of inference, we're going to focus on distributions of quantitative variables. When these outcomes are quantitative, the variable is called a random variable. And by random here we mean that outcomes are uncertain in the short run, but they have a regular distribution or a predictable pattern in the long run. Now in statistics, we often reserve the term random variable for quantitative variables. And this can be a little bit confusing for students because categorical variables can also describe random outcomes. So just be aware when we use this word random, typically referring to quantitative variables. Now, what we want to do next is talk about features of a probability distribution. And there's essentially 3 that we care about, 3 or 4. The first one is that the outcomes described by the model are random. And we just described what we mean by the word random. Secondly, the model provides a way of assigning probabilities to all of the possible outcomes. So for each outcome that we have, the model that we're using, the distribution that we're using, needs to give us a way to assign a probability to that outcome. Third, the probability of each possible outcome can be viewed as the relative frequency of the outcome in a large number of repetitions. So once again, we're talking about conducting an experiment many times and then looking at how frequently, relatively speaking, each outcome occurs. And then finally, and we just saw this in a previous slide, the sum of the probabilities of all of the possible outcomes must be equal to 1. So here are 4 features of a distribution, a probability distribution, that are going to become important. You may be wondering where they come from, and typically speaking, we generate them empirically through repeated trials. So in other words, we might record the relative frequency of each outcome and then look at the distribution of the relative frequencies for all the possible outcomes. We can also use mathematical models to represent distributions. In this case, we have to make assumptions about how outcomes will be distributed. In other words, we can use a mathematical formula to describe the predicted relative frequencies for all possible outcomes. In this course, we tend to generally stick to simpler examples. Here's one that might sort of help you understand in a little bit more detail how a probability distribution might be important to help understand and interpret data. So this comes from a pretty well-known law called Benford's Law, which in this case can be used to detect fraudulent tax returns. So legitimate records often show a very unique and interesting pattern that isn't present in faked records or other fraudulent accounting practices. In legitimate records, the distribution of first digits can be modeled using what we call Benford's Law. And you can look this up in Wikipedia to learn more about it if you'd like. But for example, Benford's Law says that suppose you have a total income recorded on a tax return of about $20,712, and the first digit there is a 2. So Benford's Law tells us about how that first digit is distributed. We can examine a very large number of tax returns, record the first digit of total income for all the returns, and then look at the relative frequency of each of those first digits. And when we do that, it will behave according to Benford's Law. Now, not all numbers out in the real world, not all data sets behave like this, but many do. Here's an actual table of what Benford's Law predicts. You can see up here in the first row, the first digit from legitimate tax returns are labeled from 1 to 9. And then you can see here the probability predicted by Benford's Law given in the second row. If you were to add these up, these probabilities would all add to number 1. And you can see all the possible outcomes here, 1 through 9, can be assigned a probability that you see right here in the second row. Now, one way to look at this is by creating a histogram of these values. So when we do that, it looks a little bit like this. Here's the probability distribution in a histogram model. The mean here in this data set is 3.4, and the standard deviation is 2.5. So you can see here the mean first digit value here is at 3.4, and the standard deviation is 2.5, and that represents the distance from the mean over here to this bar on the right. This is about 2.5 units over. And likewise, over here on the left, this distance is 2.5 units. So now remember, this picture is just a representation of what Benford's Law predicts should happen. Let's take a look at real data to see how it stacks up. Here's a table of real data collected from about 170,000 IRS files by Mark Negrini. You can see here again the first row is the first digits of legitimate tax returns, and down in the bottom row is the probabilities predicted by Benford's Law. But right here in the middle row, you'll see the relative frequency of first digits in actual legitimate tax records. Notice how close they are in almost every single column, showing us that if we have a very large number of files, then this data set very closely follows Benford's Law. Now, if you were to compare this to fraudulent tax records, you see something very different. Here's a histogram of fraudulent tax records. Notice the stark contrast. Here the mean is 5.2, located right here, and the standard deviation is 0.9. And you can see that both on the right and on the left of the mean. When we compare these side by side, we see two very different stories. Obviously, the relative frequencies of first digits from the fraudulent data over here don't follow Benford's Law at all. And the distributions have very different shapes, different means, and different standard deviations. When you compare these to legitimate data, in fraudulent data, we are much more likely to see numbers with a first digit of 5 over here, and much less likely to see numbers with a first digit of 1, 2, or 3, compared to actual data where we are very likely to see first digits of 1, 2, or 3. When we compare the distributions here, we can get a better understanding of the standard deviation of a random variable. The distribution in which it is more likely to find values that are further from the mean will have a larger standard deviation. So if you have numbers that are further from the mean, you will have a much larger standard deviation. So the moral of the story here is that the shape, the center, and the spread of a distribution in histogram form can tell us something very important and help us make sense of data. If you were presented with data over here on the right, you would most likely not believe that it were real data if you knew about Benford's law and the distribution of real data as it appears over here on the left. That concludes our video for this time. I hope you found it helpful.